So since this is still a calculus class, we're going to start with doing the first thing that you'd imagine we do with sequences, which is find their limits. So it turns out that with sequences, there's only one type of limit, and that's the limit of the term of the sequence as the index approaches infinity. In other words, you can sort of think of it this way, that what we're finding with any limit of a sequence, we're finding the limit as n, the index, approaches infinity of an. So, and of course, like any limit, sometimes this exists and sometimes it doesn't. So that's kind of a nice thing. If you think about it, it doesn't really make sense to ask what's the limit of the sequence as n approaches 5, because since either the sequence, the index starts higher than 5, in which case that term has no meaning at all, or if the sequence starts at 5 or less, we would simply evaluate the sequence at 5, and that would be, that would be its, that's limited. There's no real clean definition of what it would mean to approach some point in the middle of the sequence. So all limits that we're interested in are limits as n approaches positive infinity for a sequence. So here's the basic engine of how we're going to evaluate that. This is the important theorem. It says that if an is equal to fn for all index values n, where f is going to be some function defined on the real numbers, whose domain is the real numbers. And if the limit as x approaches infinity of f of x equals L, in other words, if it exists and equals a number L, not if it equals infinity, not if it's undefined in some other way, but if it actually equals a number L, then the limit of the sequence is also L. So what does this say? Basically what it says is that if we have a general term for a sequence that looks something like this, like 2n plus 1 over n, we can just evaluate it the same way we would evaluate a similar expression with x. Just replace n with x and evaluate the limit as x approaches infinity. In fact, the truth is we don't always replace it with x. I'm going to do one example where we do the formal replacement with x, but really you can treat this as though you're just evaluating the limit as n approaches infinity, the same as you would if this were written in x or t or any of the other variables that we usually use for functions. So, and if that limit exists, then the number is also the limit of the sequence. That number is L above. Now, why is this an interesting fact? Why am I telling you anything other than just as we used variables like x and t and w, we can now use the variable n? I'll tell you why. There's a difference when the domain of the function is the integers, and this is what it is. It's found in what the theorem does not say, and I cannot hasten to add how many people I've watched get completely confused by this point. So I will demonstrate later what it means and a good example of when this is the case. What the theorem does not say is that if the limit as x approaches infinity of f of x does not exist, then the limit of the sequence also doesn't exist. It's very possible that you get this to be true, that when you define your function f, oops, that's not what I want to do. It's very possible that when you define your function f and get, there we go, there we go. When you define your function f and evaluate the limit, you get you get does not exist. And yet, it might be the case that the limit of the sequence still does exist and equals a number that you just have to find in a different way. So that's the thing that you have to be careful of. So we'll see an example of that, but for now, let's just do some straightforward examples where we evaluate limits of sequences using the same rules that you learned for evaluating limits of functions at infinity. This is a time not to be learning a new thing, but to be reviewing what you already know about limits of functions as x approaches infinity. So let's do this example, and this is the only one where I'm going to do it very, very formally by actually doing the formal replacement of n with x. Let's find the limit of this sequence. This is, we have is, first term is 2 squared minus 2 over 2 squared. Next term is 3 squared minus 2 over 3 squared, 4 squared minus 2 over 4 squared, etc. If you notice, the only thing that changes in each of these terms are these numbers. Everything else is exactly the same. So it makes sense to say that that's just the index. Let's just say that this is the n equals 2 term, this is the n equals 3 term, this is the n equals 4 term, this is the n equals 5 term, and we're just going to keep going. And we can now just read right off of each of these, looking at the circled elements, we can see that this is going to be the sequence. an is equal to, or right, its general term, n squared minus 2 over n squared for n greater than or equal to 2. It turns out that this is one of those rare cases where it's convenient to start the sequence at n equals 2. I would like to point out that it's not unique. In other words, I could have simply said, let's call that the n equals 1 term. That's n equals 2. In purple, I'm writing with an alternative way of labeling these, indexing these terms, in which case I could have just said this 2 is n plus 1, this 3 is n plus 1, 4 is n plus 1, because here 3 is just 2 plus 1, 2 is 1 plus 1. So I could have written it as n plus 1 squared minus 2 over n plus 1 squared for n greater than or equal to 1. And that's always the case, that there are always an infinite number of different ways that I could write the general term for a sequence, if only by changing where the index starts and adjusting the algebra accordingly, like I did here. But we're going to use this definition of the sequence. So what I want to do, the first thing I need to do is define, I don't want to write this in red, that's too scary. 1, define f of x to be the exact same term but with an x. So in other words, I have n squared minus 2. I'm just going to define f of x to be x squared minus 2 over x squared instead of n squared minus 2 over n squared. Okay. Now 2, we want to verify that f of n equals an for all. I'm going to use mathematics actually. An upside down a means for all. It's an important term in mathematics. You should learn how to use that. A couple of terms, by the way, that you should know. Upside down e backwards means there exists, and then of course we've learned this one, therefore. This 3 dots is therefore. So you already know a little bit more mathematical terminology than you did. So what we can do is note that we're going to verify that f of n equals an for all n greater than or equal to 2. That's very easy to verify, because if I write fn, given the definition of f of x, all I'm going to do is replace x with n every place I see it. And of course, looking up here, that's simply the exact definition of an. So there we go. That's we verified that fn is equal to an. So now 3, we want to calculate the limit as x approaches infinity of f of x. That's fairly easy to do, because we have the limit as x approaches infinity of x squared minus 2 over x squared. Now I know that some of you, if you've taken Calc 1 and learned L'Hopital's rule, you look at this and say, oh, that's an infinity over infinity limit. I'm just going to use L'Hopital's rule. It's kind of a waste to use L'Hopital's rule for a function that's this simple. Here what we have is we have two polynomials with the same degree, which means it's just going to be the ratio of the coefficients of highest powers. If you don't know what I'm talking about, if that phrase sounds a little bit too slick, you can just evaluate this the way that you did before you learned L'Hopital's rule. Just multiply by 1 over x squared times over 1 over x squared. That equals the limit as x approaches infinity of 1 minus 2 over x squared over 1. That equals, since 2 over infinity is just 0, that's going to be 1 minus 0 over 1, which is 1. Now, what we have found is the limit of f of x. So strictly speaking, there's one more step that we need. Let's go back to that theorem. The theorem says that if we've met all these conditions, in other words, we found that an equals fn for all index values, we did that, and if the limit as x approaches infinity of f is equal to L and exists, then we can conclude that an is also equal to that limit. We've gotten up to here. We found this the limit of f of x. Technically, we need one more step. We need to actually say, for conclude that the limit of an, that's an, also equals 1. And it does, and that's the answer. So strictly speaking, 3 is not the final step, 4 is. Now, here's the secret. Most people don't do it this way. After you learn that this is the basic framework of how to do the problem, let me show you how most people would do this. Most people would just write the limit as n approaches infinity of n squared minus 2 over n squared. They'd simply calculate it this way, and it becomes limit as n approaches infinity of 1 minus 2 over n squared over 1, which is 1 minus 0 over 1, which is 1. In other words, most people simply recognize that if you have a good general definition, and you could do this replacement with x, we don't really do it. We just use this shortcut, and it's fine. Nobody's going to say that you shouldn't do this. So that's so this is really what you have to do. I'll show you later the example where it actually matters. That's the one. That's that situation where I told you you had to be careful, but we'll get to that soon.